Welcome to our webinar, High Performance Network Security, MACsec and IPsec on Altera FPGAs. I'm Marcus Weddle with BittWare. Today we'll hear from 3 speakers and then we'll have a live Q&A session. Now, if you think of a question during the webinar, use the question chat and write out your question. I'll read it at the end and you'll hear one of our panelists answer. So let's meet our speakers. First will be Craig Petrie with BittWare. He's going to give a background of our products, including FPGA cards and servers. Next up is Seth Reinhardt with Altera. Seth will take us through the Agilex 7 family of FPGAs, which power the BittWare cards running Xiphera's IP. Of course, our featured presentation will be from Tommy Lampilo with Xiphera. This is a BittWare partner with a long history of security IP and have recently added a high-performance IPsec product in addition to MACsec on BittWare cards. So one more reminder, if you are watching this live and think of a question, just send it along either during the main presentation or after, as we will stay on to answer as many questions as we can. All right, so let's get started with Craig Petrie from BittWare.
Thanks, Marcus, and welcome to everyone watching the webinar today. For those who perhaps haven't heard of BittWare before, it's worth highlighting that BittWare is part of the Molex group of companies. Molex is one of the world's largest design and manufacturing companies, servicing major customers across a range of markets, including datacom, automotive, and industrial. BittWare designs and manufactures enterprise-class acceleration products, featuring the latest and greatest field programmable gate arrays, or FPGAs. These high-performance programmable accelerators enable customers to develop and deploy solutions quickly and with low risk. For today's webinar, we are focusing on the Altera Agilex 7 series of devices for use in telecommunications, industrial automation, and critical infrastructure. BittWare helps customers succeed by creating platform products with the FPGA at the heart. These off-the-shelf products are primarily PCI Express cards in form factors including half-height, half-length, full-height, half-length, and dual-slot GPU. However, we also support some storage form factors including M.2 and U.2. Each card or module adheres to official specifications to ensure compatibility with existing and new infrastructure. Each product features BittWare's sophisticated board management controller, or BMC, and associated software development kit. This BMC allows the FPGA hardware to be securely configured and controlled. Our most recent I-Series and M-Series Agilex 7 cards feature our new BMC, version 3, which has support for root of trust, which is essential for critical infrastructure. The IA860M is BittWare's flagship product and a good example of a platform which can be used in conjunction with Xiphera MACsec and IPsec solutions. This product features an Altera Agilex 7 M-Series FPGA supporting 16 lanes of PCI Express Gen 5. It is a dual-width, full-height 3/4 length PCIe card compatible with edge and rack-mount server platforms catering for GPUs. We've taken advantage of the groundbreaking F-tiles to support up to 3 400GB or 24 1025 or 50G network ports per card. 32GB of in-package HBM2 memory, accessible through a high-performance network on chip, or NOC, delivers 800 gigabits per second of memory bandwidth, aiding buffering, flow control of network traffic. The 860M and other BittWare cards can be purchased individually or delivered pre-integrated in servers which have been optimized for FPGAs. BittWare designs specialized servers with extremely high densities of FPGAs and network connections, as well as leveraging standard server products from the leading providers listed here. In both scenarios, a single comprehensive warranty is provided, allowing customers to rapidly deploy proven systems in volume once the proof of concept phase has been completed. Many of our customers program their own application on the FPGA using either an RTL language, such as VHDL or Verilog, within the Quartus tool environment. Some use newer abstracted tool flows such as OFS or OneAPI. For those customers who wish to forgo the programming of the FPGA entirely, they can purchase BittWare's FPGA accelerator cards pre-configured with applications from domain experts, including Xiphera, via the BittWare Partner Program. This model for deploying FPGA-based solutions is highly recommended since there is no need for the end customer to program or manage the application bitstream themselves. A proven, documented, and supported solution from a partner such as Xiphera is the quickest and lowest risk path to deployment for our customers. To help explain more about the capabilities of the Agilex 7 FPGA at the heart of the BittWare card, I'll now hand you over to Seth from Altera. Seth, over to you.
Well, thanks, Craig. I appreciate that. I always appreciate it when an Altera device is at the heart of a BittWare card, or at the heart of any system for that matter. My name is Seth Reinhardt, and I'm a technical marketing manager here at Altera, looking after security solutions. And for the brief time that I have, I'm going to go through a few slides, primarily covering at a high level Agilex 7, what it is, a little bit of double click on the M series, which is the heart of the IA860M BittWare card, and then I'll talk a little about Altera's solutions related to security, again high level, but I just want to give you a sense of what we've been working on in that space. On this first slide here, we see a cartoon of Agilex 7, specifically the M series. And in fact, with these blocks that are shown, there are quite a few capabilities that the M series brings over and above its sister subvariants. The next slide we'll talk about the F series and the I series, and with the M being the newest with the most capabilities. Notably, the red block there, the HBM2E, is DRAM co-packaged with our FPGA fabric, connected through an EMIB interface, which is essentially a very wide, very high bandwidth memory interface to access the DRAM. And there are some other notable upgrades. So, for example, DDR5, LPDDR5 are new for this device. The NoC, the network on chip, is primarily responsible for making sure that the memory bandwidth is taken advantage of, and that bottlenecks are eliminated between these memory subsystems on the bottom and top there, between those guys and the fabric. And finally, I'll mention that we've moved to the Intel 7 process for the M series for faster performance and better power. All right, so on this slide, I'm just going to talk briefly about the Agilex 7 family by way of its variants. There's the F, the I, and the M series. M series we've talked about a little bit, but I'll start with the F series. Very capable family member, many device options, and a very fast fabric, which includes 58 gig transceivers, PCIe Gen 4, DDR4 interface, and a very capable ARM Cortex subsystem. But moving to the I, we add 116 gig transceivers, we upgrade the PCIe to Gen 5, and we add the coherent CXL interface to pair with the Xeon processor. And we've covered the M series, but just to hit in the prior slide, but just to hit those high points again, it includes the 116 gig transceivers. We upgrade, it includes the PCIe upgrade to Gen 5, but we also upgrade the memory interface from DDR4 only to include DDR5 and LPDDR5, and of course the massive 16 gigabyte or 32 gigabyte memory option by way of the HBM2E co-packaging. Okay, so on this slide, I'll talk a little bit about security. From the Altera perspective, kind of over the years, this is a bit of a timeline or a map of features that we've added along the way. Starting with ARIA, we added bitstream authentication, anti-tamper sensors in response, A big add in Stratix time frame was the SDM, the Secure Device Manager, which I'll talk about a little bit more on the next page. Puff keys, so physically unclonable function, which essentially is, the physics and, the uniqueness of every device becomes the key, a key. So each individual device can be authenticated separately, individually. The next Agilex 7 and 5 add quite a few features as well. But today's focus being 7, we've added hardware attestation and cryptographic services, black key provisioning, just to name a few. There are several other things under the hood. I would just encourage you folks to, take a longer look at what we're doing in security and ask the question how you're securing your device and enhancing your security profile. Okay, so last slide here. I wanted to show you a quick block diagram, kind of a high-level block diagram of the SDM, the Agilex 7 Secure Device Manager. And yeah, it's not particularly, doesn't seem that high level, although each of these blocks have quite a bit going on underneath them, and more importantly, the software and the solution that wraps around them. But the SDM itself, it's a triple redundant MCU core for resiliency and maximum uptime. And it manages all these blocks and in fact talks out to the FPGA fabric. The orange and yellow block on the left represents a number of hooks throughout the fabric that the SDM manages or talks to. So for example, SEU detection, single event upset, or partial reconfiguration, temperature and voltage sensors, etc. And note in the middle there, the crypto IP, so cryptographic services have been enhanced. There's a number of IP blocks in there that are used for various capabilities. All right, so with that, I'm going to pass the mic over to Tom. Tom, I'm looking forward to hearing more about what Xiphera is offering. I know you're going to do a quick high-level overview, and then, of course, double-click on today's topic. All right, thank you so much, folks.
All right, thanks, Seth. My name is Tommi Lampeland. I'm the Chief Revenue Officer for Xiphera. As background, I have somewhat over 20 years in the cybersecurity industry, and I worked on security solutions based on various different security protocols, out of which we'll be covering two today in more detail, MACsec and IPsec. Our customers are looking at implementing security protocols to meet various different security requirements and challenges, ranging from the baseline data confidentiality, integrity, and authenticity to mitigating the quantum computer threat with post-quantum cryptography. Also, the number of devices connecting today to various edge, cloud, and AI environments is strongly and rapidly growing, and of course the connectivity between these devices and these various services and environments needs to be secured. And there are also different legislation and compliance mandates relating to, for example, IoT security with, for example, the European Cyber Resilience Act mandating the management of security of IoT devices throughout their life cycle, as well as government mandates, for example, in the US, the drive to secure critical environments with post-quantum cryptography over the next few years. We'll be looking at the building blocks out of which we compile and build these protocol implementations. But first, let's take a look at the OSI model, the Open Systems Interconnection model, which represents network communications as a stack of layered logical layers, ranging from the application layer all the way down to the physical layer, with the physical layer representing the actual devices or the hardware that executes the connectivity, whether it's physical wiring or wireless components. We'll be focusing especially on two layers: the data link layer and the network layer on top of it, and the MACsec and IPsec protocols that secure traffic on these corresponding layers. Now, each of the layers in the OSI model interact with the layer on above and beneath the layer in question, and communicates with the logical layer on the other side of the communication. Xiphera offers a quite wide portfolio of hardware security IP, ranging from traditional cryptography all the way to post-quantum cryptography and different cryptographic primitives, out of which we build the protocol implementations. I won't be covering all of these in any great detail, but we will be focusing, as mentioned before, on the IPsec and MACsec protocols, and we'll also take a look at the AES GCM encryption algorithm, which acts as the encryption engine for these protocol implementations. So let's start by doing that exactly. Well, AES GCM stands for Advanced Encryption Standard in Galois Counter Mode. It's a block cipher of 128-bit block size. It's good to note that block size doesn't correspond to key length, so we can have key lengths longer than 128 bits, and I'll come back to the key length question as we go forward. So AES is pretty much the workhorse or engine that encrypts bulk traffic as the core component of these security protocols, and it's a very efficient method to guarantee both confidentiality and also authenticity and integrity of the data being transmitted. We add with the Galois counter mode, we add also data integrity and authenticity to AES. So we're not only encrypting the bulk data, but we're also authenticating the associated data, for example, header information. So we're basically combining AES counter mode with the Galois message authentication code to provide a comprehensive security within the protocol implementation itself. And AES GCM offers these security services combined with high performance capabilities. So it really is a natural choice for the security engine of protocol implementations. Coming back to the key length question, so I mentioned that we can use key lengths of various size with AES GCM, but we do recommend the minimum key length of 256 bits currently, as a symmetric cipher. AES GCM is not immune to attacks by quantum computers, but increasing the key length to a minimum of 256 bits effectively protects against attacks by quantum computers as well. Looking at our implementation of AES GCM in our IP core offering, we have fairly recently released an extreme speed variant of AES GCM, which is built on a parallel and fully pipelined architecture for maximizing throughput. So we're really pushing data through and securing it as efficiently as possible. The implementation is of fixed latency, so it's easy to integrate into the overall design, whether it's a security protocol or other security solutions. And like I mentioned, AES GCM is used as the engine in various different security protocols, including IPsec and MACsec as the default crypto engine powering the secure communications. So let's jump to the looking at the security protocols themselves. We can first take a step back and take a look at the various different applications that these protocols are used to implement. And these are just some examples of typical implementations of MACsec and IPsec, and these are not set in stone in any way. So when planning your protocol implementation, you pretty much have the options of looking at both protocols, and depending on the overall environment into which the solution will be implemented in, typically one of these is the more natural choice. MACsec, for example, is often a choice for securing automotive backbone connectivity to secure the traffic between the various components in today's networked vehicles. It can be used to implement security in Open RAN architectures and 5G networks, and is often the choice for mission critical and industrial environments to secure, for example, control traffic in these systems. IPsec, on the other hand, is typically used to secure traffic between networks and is often used to implement, for example, gateway to gateway VPNs between different sites and networks. It's also often offered as a smart NIC implementation based on FPGAs. MACsec, the MACsec protocol resides, like mentioned, on layer 2, the data link layer, and stands for medium access control security. It's a relatively young standard compared to some of the other security protocols, in that the latest standard version is from 2018, and it's designed for securing Ethernet port-to-port traffic with AES GCM. Where, again, confidentiality is taken care of by the AES counter mode or AES encounter mode, and integrity with the Galois message authentication code. MACsec can be implemented or in multi-hop environments as well, with certain extensions to the protocol. Now, the protocol supports key lengths of 128 bits as well as 256-bit keys, but we do, like mentioned before, we do strongly recommend 256-bit key lengths. Key management in MACsec is not in defining the protocol specification itself, but there is a companion protocol, 802.1x, which defines key management that can be used for MACsec. Taking a look at our implementation of MACsec in our IP core offering, we offer different variants of the protocol, optimized for different scenarios and network environments, depending on whether you're optimizing for size of implementation, as in area footprint of the IP core, or for high performance and throughput. So we offer a balanced version for single gigabit traffic, a high speed variant for tens of gigabits, and then an extreme speed variant for hundreds of gigabits throughput. The extreme speed variant is based on parallel streaming architecture with fixed latency, again, for easy design integration. And it's a full duplex implementation, meaning that the send and receive paths are fully independent of each other, so we can optimize it for different use scenarios. So now going to IPsec, which resides on the network layer on top, being the layer 3 in the OSI model. IPsec standing quite naturally for Internet Protocol Security. Compared to MACsec, IPsec is a somewhat more complex standard, or in reality a set of standards, as it's defined in over 70 different IETF RFCs. That have been drafted and specified over several decades, and it offers multiple algorithm choices for implementing both key exchange and data traffic security for both encryption and the authentication. However, for the bulk data encryption, the implementations are pretty much converging on AES GCM, which is a natural choice for the bulk data security. Key negotiation, key exchange, on the other hand, is implemented by the IKE version 2 protocol, the Internet Key Exchange Protocol, and this is typically almost always implemented in software as opposed to uh, pure RTL implementation on FPGAs. If we take a look at our implementation of IPsec in our IP core offering, we actually released IPsec in March, a couple of months earlier. And again, we've designed the implementation for scalability. It's suited for implementations from 10 gigabits per second to 200 gigabits throughput on high-end FPGAs. And like I mentioned, IPsec is based on a wide or a large number of different RFCs and kind of optional ways of implementing the protocol that partially complement each other. So we've started out with implementing the ESP, encapsulating security payload, frame processing, again using AES 256 GCM for the traffic encryption. It's based on a streaming interface for payload data and side channel signaling for setting the ESP frame parameters. And again, the transmit and receive channels are completely independent of each other for flexible implementations. So let's compare these two protocols with each other as a kind of a summary. So when we look at the standards, MACsec is a quite well-defined standard and a cleanly defined protocol, whereas IPsec again is based on a pile of different optional RFCs. So this means that interoperability for MACsec is quite straightforward to implement, whereas for IPsec it's a little bit more challenging. You really need to have an understanding of what kind of IPsec implementations you need to interoperate with, and then ensure that with testing and the implementation, and also you need to define quite clearly what you mean with IPsec. How are you going to put it together? What are the requirements, and what is the environment that it will be implemented in? And then choose your selection of the IPsec specifications on which you base your implementation on. Key management, again, in MACsec, it's defining the 802.1x standard. That's an optional a companion standard to the protocol itself, and in IPsec, it's implemented in the IKE version 2 protocol. Key management for both protocols is typically implemented in software as opposed to RTL on the FPGA. IPsec is defined is designed for multi-hop environments and traffic between networks. And in MACsec, you can implement multi-hop with what's called EDE modes and extensions to the protocol itself. MACsec is fully based on only the AES GCM cipher, whereas IPsec does offer multiple options for implementing encryption, but in practice, the implementations are converging on the AES GCM cipher. The two, like we saw when examining the OSI model, the two protocols reside on different layers in the TCP/IP stack, where MACsec resides below the IP layer, and IPsec between the IP and TCP layers. When we look at implementing these protocols on FPGAs, MACsec implementations, again, based on whether you're optimizing for performance or implementation size and footprint, we can implement MACsec starting from implementations starting with at 14K lot, whereas IPsec pretty much takes 50K lots per 100 gigabits of throughput. per second. And pretty much the driving factor of which protocol you decide to go with depends on your use scenario and the environment that the implementation will reside and operate in. MACsec is typically used for closed systems, industrial environments, for example, and IPsec for implementing security for network-to-network traffic. And again, these are not set in stone, but rough generalizations of typical protocol use. I mentioned the threat of quantum computers when we started out, and like I mentioned, in order to protect the bulk data encryption, the symmetric encryption against quantum computers, you need to use key lengths of at least 256 bits in size. But the component most threatened by quantum computing is the asymmetric algorithms used for key exchange, for example, and digital signatures. And why we're already concerned about quantum computers? Because as far as we know, the implementations of today are not yet strong enough and stable enough to compromise our existing security infrastructures. Is the fact that malicious actors are most likely already targeting and capturing interesting data and internet traffic and storing it for the purpose of then decrypting it when they have access to powerful enough quantum computers, this being the harvest now, decrypt later attack. So any data that we already process and transmit today that we want to keep secure and confidential for the next 10 years, 20 years, or throughout our lifetimes already should be protected by post-quantum cryptography, which is a form of cryptography and a set of algorithms that are secure also against attacks by quantum computers. So how does this affect the protocols we've discussed today? Well, in the case of IPsec, IKE version 2 as an RFC has a draft proposing implementation of MLChem key exchange, quantum resilient key exchange as part of the IKE version 2 key exchange method. MACsec in itself, the protocol specification, does not implement asymmetric cryptography within the protocol itself, so it's secure for the time being. Of course, you need to take a look at the key exchange implementation for MACsec as well. So when you're looking at implementing the security protocols, you obviously need hardware to run the protocol on, and a great choice for implementing Xiphera is MACsec or IPsec. IPs is the range of BittWare PCIe cards based on Altera Agilex FPGAs, and with these cards we can provide, for example, IPsec throughput of up to 200 gigabits or more on a high-end card. And you can find more information on these on our partner page and obviously BittWare's site. And with this, I would thank you and hand back over to Marcus and BittWare for our Q&A session. Thanks very much for being here today.
All right, let me switch over to our live question here. As I do that, I just wanted to say, well, thanks, Tommy, for that. And we are switching over to our Q&A. So again, if you are going to ask a question, just type it out and I'll put it to our panelists live. Let's see, and we'll stay on as long as the questions keep coming, so no worries there. I did want to thank our panelists for their contributions. I know from the BittWare perspective, having partners like Altera and Xiphera is just an excellent relationship. It really gives our shared customers a solid, reliable product and solution they can rely on. So with these latest high-performance IP cores, I know many of you are excited to have more options, including, as Tommy was saying, the latest IPsec and, of course, MACsec. And so some questions have come in, some more detailed than others, but I hopefully this is valuable to you. So let's start with Craig. First of all, Craig, can you hear me okay?
Yes, I can.
Okay, great. So I guess the obvious question, can I buy the how do I get Xiphera's licensing? Do I get it from BittWare? Do I buy it from Xiphera? And maybe some pricing information.
Sure. Yeah, in terms of the options for customers, obviously there's different phases they go through, from proof of concepts to volume deployments. And Xiphera have got a very flexible set of terms and conditions which allow customers to effectively customize the purchase to suit their project requirements. So Tommy can talk about that in more detail. Well, fundamentally, you can purchase the BittWare hardware, and you can also purchase the Xiphera license through BittWare. So one of the reasons we set up the BittWare partner program was to de-risk the experience for customers. Rather than purchasing everything separately, having to prove it together yourself, what we've done with the Xiphera team is we've made sure that we've done some testing with their IP on selected cards. So the cards we support at the moment are the IA420F and IA840F cards. And you can purchase the hardware and the Xiphera license from BittWare through the partner program. So it simplifies purchasing and provides an overall better customer experience for people who want to test the IP and then deploy it. Tommy, I don't know if you have any additional comments on that question, perhaps around just the types of licenses that customers can purchase.
All right. So hoping everyone can still hear me. So basically,
good. Thank you.
The license and pricing model is fairly straightforward, and BittWare can certainly quote you on those. It basically depends on two factors: the volume of cards and licenses that you're purchasing, as well as basically the speed grade of the IP. Whether you're going for the extreme speed variant or if you can make do with the balanced or high speed variant. So those two factors, volume and speed, are the deciding ones.
All right. Let's switch from kind of a higher level pricing and stuff questions to a very technical one, if you're ready for this. And I know, Tommy, that you have someone else from Xiphera on the line too. So either one of you feel free for this one. So what is the scope of the IPsec IP? Are there any other integral parts of IPsec included, like SPD, SAD, replay protection, UDP and cap, routing lookup, ARP lookup, etc.? So hopefully you can address some of that.
Alrighty, I think for most of it, I think I will pass it to our lead architect, Tuomo Tarvanen, who I luckily have as a backup online as well. As I mentioned during the presentation, IPsec is quite a multi-headed beast in the way that it's defined in over 70 different RFC documents, and there's various ways of putting it together. But I'll let Tuomo address what we have currently implemented in our IP core, and then obviously we are able to take that implementation and adapt it, modify it to various different scenarios and depending on the customer requirements. But I'll let Tuomo address what we currently have implemented in the baseline release itself.
Okay, thanks. So what we have currently is the code name is XIP 7013E, and there's information on our webpage about that broad brief. And that is ESP frame protection IP. So it can be used either in tunnel or transport mode to protect the ESP frame. So it handles the header and the ESP frame itself, both decryption and encryption. And it's scalable from 128-bit data bus up to 1024-bit data bus. But it doesn't include any kind of, for example, in tunnel mode, this Altera IP header generation or UDP encapsulation. So those needs to be done additionally there, and that is one further development what we have ongoing.
All right, thank you for that answer. I've got a question. Maybe this one's probably for Seth at Altera. So you talked about the security on the chip, and I guess that's the security of how does that relate to the IP cores from Xiphera? Because you've got security on the chip, then you've got these IP cores running in the fabric. How does that kind of relate?
Yeah, thanks. It's they certainly are complementary. The focus of today's webinar and the SDM, which I talked about, the Secure Device Manager, is responsible for a number of things that really relate to overall chip security and ultimately your board and your system. But the SDM is doing things like it's doing bitstream encryption and authentication, attestation, just to make sure it is the IP that in fact you want to be running on your system, plus anti-tamper sensors and side channel attack protection, SEU management, so single event upset if a bit gets flipped, what to do, how to correct that, or if multiple get flipped in a really high intensity environment, voltage spikes or radiation or things like that. The SDM, being a triple redundant lockstep core, is able to keep its head no matter what, and reconfigure sectors within the chip as needed. And there are some other more subtle kind of sub features to that, but that's just kind of the overview of what the SDM does. And really, today's focus is all about secure comms and making sure your data is protected. And the SDM is much more about the chip level, kind of the system integrity.
Right. I appreciate that. That's another question probably for Xiphera, and this is there was some discussion about post-quantum protection. So this question, what post-quantum signature algorithms do you have accelerators for, and how does this relate to the NIST standardization track?
All right, thank you. So we have started our post-quantum journey with implementing out of the signature algorithms MLDSA, formerly known as dilithium. That's basically has been selected by NIST as the lead algorithm for digital signatures in the ongoing standardization track. That was published as a draft standard, I believe, back in August, and we are waiting, of course, for the standard to be finalized. But MLDSA will definitely be part of that standard, and we do have an IP core available for that in our portfolio.
And just a brief follow-up on that. With your other IP cores, are you primarily focused on FPGA fabric and some of those other IP cores, and kind of where do you see the future, 1, 2, 3 years from now for the company? Faster FPGAs come out, you support them, but just walk me through that briefly.
Yeah, so we do. I mean, FPGAs obviously are a kind of where we originate from, and we do continue following the development in the field. Our implementations of our IP cores of the various protocols and algorithms are implemented to be in a way generic, that they are easily applied and implemented on a range of FPGAs, and are expected to support future generations as well with little or no modifications. Relating to post-quantum crypto and FPGAs, one of the great advantages of FPGAs is the fact that they are reprogrammable. And that gives us what we call crypto agility. So as the PQC standards are still in the standardization track or process, kind of work ongoing, even though we have a pretty good feel for what the standard and the selected algorithms are and will be, there's a possibility that something will change and some algorithms will be added, some may be dropped if a weakness is found late in the game in one of them. So having FPGAs as part of your design gives you the advantage of being able to update your implementation of cryptography from traditional crypto to post-quantum or into hybrid scenarios, or updating even the PQC implementation on board. So that does give that gives a great advantage to any solutions incorporating FPGAs down the road.
Mm-hmm. I appreciate that. And I've got a question. Actually, I'm going to kind of combine two questions as they might relate enough. The first question is about, so I'll just read it. How does this compare with the hard IP for AES as far as LUTs per gigabits per second? And then another question, how does the Xiphera MACsec solution at 100 gig differ from Altera's 100 gig softmac solution? Are there any hard IP cores on the Altera 7 devices that can assist with MACsec? So maybe, I don't know if those are different enough or similar, but I'll let you answer that.
Okay, I think that's I think those questions, I think we'll take them one by one, and I'll probably ask Tuomo to step in to give some maybe examples of our AES implementation, sizing, resource consumption, and performance on Agilex. So, Tuomo, do you want to address that?
Okay, first of all, this size, if we compare this Altera crypto IP hard block there, it's capable for, according to my knowledge, to 200 gigabits a second. And basically, if you are implementing AES GSM as a soft IP, what we have currently reached, it's about 100,000 ALMs what you need for same performance there. So with let's say Agilex 5 with the highest speed grade, you can reach about 450 megahertz with 512-bit interface, but you need to have 100,000 ALMs for that, and that is taken. Of course, when you are using the crypto IP, you are saving that. Of course, the thing is that if you want to have a full duplex thing, then you need to have two crypto IPs there, one for the ARX and one for the TX. So, of course, if you need to have multiple interfaces, then might be that after all the with single FPGA, then you need to use soft IP anyway, because you don't have enough crypto IPs there. That is one option there. Other option is that, of course, the crypto IP is not available in every FPGA from Altera portfolio, so there's also variants which don't have crypto IP. I hope that answers the question.
Yeah, I'll just chime in and say that that's exactly right. I agree with all that.
Okay,
Thanks.
and did that speak to the second question as well?
Maybe. What was the second question?
Right, I think it did. Yeah, this was the question. How does the MACsec solution from Xiphera at 100 gig differ from the Altera's soft MACsec solution?
It does. Yeah, it does address that a bit. Xiphera is being, flexible if you need multiple interfaces, evolution and changes and things like that. Being an IP company, it definitely more focused on those types of details, soft flexibility, and keeping up with the latest and combining standards and such.
Yep. All right, I've got a question for, let's see. Oh, this would be for Xiphera as well. Okay. Is the core itself available as open source if I want to compare it to, for example, the Intel, MACsec card? My main concern is always black box crypto, which I cannot use. Are there any other notes on how FPGA IP solutions compares to one of the COTS IPsec accelerator cards?
Right. Yeah, I can address that. So we, but by default, we license our IP cores as encrypted RTL, but there is a licensing option also for licensing the plain text source code if you need to do a review or do certification or some other modifications on the code itself. So that is an option, but it's a licensing option from us. We don't release it as open source on the web as such. Yeah.
But I guess that leads me to a question that I had that I can kind of rephrase, such as, there are other IP sort of versions of this around in different forms, and what do you find your customer base, because obviously you are deploying this in the MACsec world for a long time now. What do you find really makes customers jump on this particular implementation on FPGAs, and just kind of directionally, what makes a customer a good fit for this, if that makes sense?
Right. Well, it's on one hand, it is the adaptability and the support that we can give our customers on. So we do want to have a very close interaction with our customers, basically acting as a kind of a outsourced R&D arm, focusing on the implementation of cryptographic IP on their products. On the other hand, our IP cores are highly optimized in terms of resource utilization or throughput and performance, depending on what weighs more in your requirements. And the IP is also pure RTL logic design, so there's no embedded CPU or software components inside, which gives you advantages in terms of streamlined architecture, performance, security in terms of smaller attack surface, and also ease of validation, as you don't have CPU or software components to validate as part of your IP solution.
And just another question that I know that I have spoken with you before about, Tommy, and that's just in deployment. Do you typically see either MACsec or potentially IPsec on a single card in a server, or does it typically get deployed on a bunch of FPGA cards in the server? In other words, is it more of a smart NIC for the whole box, or does it tend to be? I guess that would change whether it's more of a MACsec local, or just kind of briefly talk me through that one too.
Yeah, so it does depend on the use scenario. Not sure if Tuomo has some comments on what would be the optimal implementation model for a let's say a specific use case. Tuomo, do you have any comments on that based on what we've seen?
Well, the typical use cases are, for example, this kind of add-on cost that, for example, like securing the traffic between the data centers and, let's say, office to office or building to building. And then there's other like custom cases which are really like a special hardware designed by the customer, where they want to have some security solutions there. But I would say that for the MACsec, the most common is this kind of like point-to-point protection building to building or office to office. Or
right. All right, I've only got a couple more questions queued up right now. If anybody else on the call wants to ask, make sure you type it out, and we'll get it. But winding down here, this question I can't recall if we've asked and answered this before, but just Craig was talking about the 860M, and we have the F series cards, the I series cards. The 860M is a much larger, more powerful in many ways. So, can you go to 400G on a card like the 860M and just kind of talk me through bigger, faster? What does that look like?
Right, I think I'll let Tuomo estimate that as well, if you can on the fly for the 860M.
yeah, so a little bit covered that already. So it really depends about the FPGA, that if you what is the speed grade, what do you have on the board. So this kind of 400 gig that can be reached with the ASGSM level, but when you integrate this like IPsec on MACsec, then it gets much more complicated. So 400 is a little bit like out of reach at this moment, but we are trying to optimize that. 200, 300 gig is doable quite easily.
Okay, that's fair enough. I've got another technical question here. I'll just read it out. For MACsec, what are the limitations with regard to frame sizes? So for 100 gig MACsec link, what's the smallest frame size that is needed to keep up with full rate decryption and authentication?
Okay, so that is MACsec is designed so that this fully parallel implementation and streaming implementation. So we don't have any, in practice, we don't have any kind of idle cycles there. So of course there's an overhead from the protocol. So all the bytes what the MACsec protocol is adding there. So that is limiting that. Other thing which is limiting is of course the preamble SFD, CRC, and inter-packet cap added by the Ethernet MAC. But otherwise, it's working like let's say, well, typically line rate is used as a term, so it can use run at the line rate. So if we are using, for example, 100 gig and using a 512-bit interface, then we are running at 190 megahertz and a little bit more. So.
All right, I appreciate that. Let's see. I think maybe just one final question, and it's about the quantum threat, and you mentioned some mitigation concepts. But how sure are you that is going to be sufficient? Is it something that in the quantum threat sort of world that you are very familiar with? Is there a surety about those particular, symmetric and the levels of encryption, or is that kind of a hopeful, or just what's the outlook there?
Well, so basically there we are relying on the global cryptographic community and the science behind it. So those algorithms that are being standardized at the moment are being subjected, or already have been subjected to years of hard scrutiny and analysis. And based on the common understanding of today, those are expected to be secure against quantum attacks, as well as the symmetric existing traditional symmetric algorithms when used with at least 256-bit keys. So that's obviously a field that let's say the entire international cryptographic scientific community is following very closely and very actively discussing and analyzing in various forums. So the current emerging standards are based on the best of today's knowledge, and obviously will be updated if something new is identified and found. But that's basically the I think the best available knowledge that can be relied on is what's out there today.
All right. Well, I think we need to wrap it up at this point. I appreciate all the answers. Thank you, Seth, Craig, and Tommy, for all that great information. Anybody who is still on the call, we will have a recording of this made available to you. Certainly, you can follow up with us with any further questions. Thank you again for our presenters. Thank you for attending. And we will send out the recording link very soon. So thank you for watching.
Thank you, Marcus, and everybody else.
Thank you.
Thanks.
You are welcome. Thanks.